theoretical physics. First of all, I would like to say many thanks for the invitation and for the possibility to present my scientific results. And we will discuss the geometric properties of quantum states which are known as quantum graph states. And during this talk, we will discuss properties of quantum graph states which can be represented with directed and weighted graphs. The outline of my talk is the following. So first of all, we will discuss quantum states, quantum graph states. What does it mean that we have quantum graph states? Then we will consider entanglement of quantum graph states, the geometric properties of these quantum states, and then I will show the results of quantum calculations, the results of calculations on quantum devices. So, well-known structures, graphs. So, if we have nodes and we have links between these nodes, we have a structure which is known as graph. Graphs can be very complicated and with many nodes and many different links. And it is very interesting to study this structure, these classical structures, with the help of quantum programming. This purpose, we map these graphs to a quantum state. So in quantum mechanics, we know that there are different states, for instance, quantum states corresponding spin systems with Ising model presented in this slide, or some other states constructed with 2-qubit gates. It can be the various 2-qubit gates. In this slide, you can also see this RXX 2-qubit gates, which act on some initial state. And the quantum state can be called as quantum graph state if we know that the state can be represented by a graph. So if you have a classical object, if you have a classical graph, and we have some quantum protocol for preparing quantum state, we can map our graph with this quantum state, for instance, in the following way. We can say that for each node, we have correspondence to qubit. So each node in this graph corresponds to qubit. Node 0 corresponds to qubit 0, and so on. Then we can say that each link in this graph corresponds to the action of the 2-qubit gate. So if we have a link between node 0 and node 1, we have that in our protocol, the 2-qubit gate U01 acts on the state of qubit 0 and qubit 1, and so on. Then, if we have more complicated graphs with weights and directions, so if we have arcs, we can also specify this in our quantum protocol. So we have that the direction and the weights can be represented with these parameters A01, A03, A02, and these parameters we have also in our 2-qubit case, in our 2-qubit gate, which acts on our initial state.
Hello, Professor Gnatenko, can you hear us?
Yes, I can hear you, I see you. So let's discuss the quantum graph states which correspond to undirected and unweighted graphs, and then discuss these quantum graph states corresponding to weighted and directed graphs. But before sharing with you the results of our studies, I would like to highlight that studies of quantum graph states are important because they are highly entangled states. Also, they often used in quantum error correction algorithms. They are used in quantum machine learning algorithms. They used for studies of graph properties. We have different various applications of these studies, and let's start with the results. So, first of all, we will discuss about geometric measure of entanglement, which is defined as follows. So it is defined as a minimum squared for any study distance between an entanglement state and non-entanglement state. And this definition was proposed in this paper. But with the help of this result presented in this paper, published by Tkachuk, Samar, Lishak, we have a relation of this entanglement with mean value of spin, with mean spin. And also in this paper, the result for mixed and pure states is present. So if you're interested, you can look on this. But in our presentation, my presentation, I will use just this result from this paper. Then if I would like to find the geometric measure of entanglement, I have to prepare, first of all, I have to prepare the quantum states, and I have to measure the mean value of spin. So to measure the mean value of spin, I have to rotate my state and then measure the state of qubit, for instance, qubit 1, in the standard basis. So what about entanglement of quantum graph states corresponding to undirected and unweighted graphs? These results were already presented in the previous conferences, and I would like just to highlight that we considered quantum states corresponding to the Eisen model with the initial state 000 state, and we also considered controlled phase gates as two qubit gates that are used for preparation of this quantum graph state. And we obtained that the entanglement is related with the vector degree. So we have a relation of the entanglement of quantum characteristic with the property of quantum state. So if you are interested in details, please look on these papers. So the first one is published by Professor Tkachuk and me, and the second one is published with my PhD student Natalia Suslovska in this journal. So let us consider weighted and directed quantum graph states that are constructed with action of RXX gates. So we also have Eisen model, but here we consider not just 000 state, but we consider a general case when we have a state of this arbitrary parameters. So we have general case and qubit state. Then we also do not specify the action, the graph, and we do not specify these products here. We just consider general case. So we have arbitrary quantum state which corresponds to arbitrary graph, quantum graph state which corresponds to arbitrary graph. And then in this case, we can find the entanglement of the qubit with other qubits in this multi-qubit quantum state, and the entanglement depends also on the parameters of graph. But in this case, if we have directed graph, we have to specify, we have to say the number of links which go from our node or link our node with other nodes. So in this case, we have the direction from 0 to 3, and the number of links which come to our node. So we can specify this direction. So in this case, therefore, we have these parameters n with index k, which corresponds to the node in graph with index k, and this one therefore is the same, but in which ingoing and outgoing from our node. So we have this specification. So it's very interesting that also we have that quantum properties are related with properties of graphs. So we also studied this property with the help of quantum calculations, and we considered a simple model. This graph, this directed and weighted graph. So we have these directions from 0 to 1, from 1 to 2, and the weights corresponding represented by these parameters. So you can see the protocol for prepare this quantum state. So we have 2-qubit quantum gates with these parameters, and we have the initial state, arbitrary initial state prepared, and we study the entanglement of qubit 1 with other qubits. And we have done these studies with the help of our simulator. So I would like to say that we have the results of calculations with our simulator and results of theoretical calculations. The results of calculations on our simulator are represented by crosses, and the results of theoretical studies are represented by black and white colors, so gray color. So we can say that we have a good agreement of our results, and we have the lines corresponding to the maximum value of entanglement, which is 1/2 in the case of geometric measurement. Also, other results of other studies for other parameters. So we have, in order to discuss and to analyze the entanglement, even in this very simple case, we have to analyze dependencies on all these parameters. Therefore, you have these plots. So more details are presented in a recent paper published in Physics Letters A. If you're interested in this paper, in these results, you can look on this paper. Then, what about other more complicated properties, which are geometric characteristics of our quantum states? So first of all, let us discuss the model once more again, and then we will consider this characteristic. So we consider Eisen model, consider the following Hamiltonian. We consider the evolutionary quantum state, which is also quantum graph state. So we have this state, this evolutionary state, but we can represent this state because we have just Eisen model. So we can present this exponent with this Hamiltonian as action of RZZ gates on some initial state. And then we can study the velocity, curvature, and torsion of quantum states. So let's start with unknown value for you. It is curvature. So the curvature can be defined in this way. So the curvature is related with the mean values of the Hamiltonian in different powers. So this result was obtained in this paper. So in order to find this value, in order to find curvature, we have to calculate these mean values. The torsion also is related with the mean values of Hamiltonian. So you can see in this slide, so the torsion is a deviation of evolution state vector from a plane of evolution. So this was considered in this paper, and this result was derived step by step in this paper. The same for curvature. So then let us discuss how to find these values in the case of quantum graph states, and how to calculate these values with the help of quantum programming, and why do we need to study these properties. So let's start from the beginning. So let us consider the initial state to be plus state. So we have the proposition of all the basis states. Then let us consider the mean value of the Hamiltonian. So we have, because Hamiltonian does not depend on time, as we have this expression, we can write this quality. Then The velocity of quantum evolution is determined by the value of h squared, and it is very important that if you calculate the velocity, even the velocity is a simple characteristic, we have that this characteristic, or the mean value of Hamiltonian squared, is related with the sum of weighted degrees of node I graph, but in graph which is characterized by adjacency matrix with element squared to that we have in our graph representing our graph state. So if you consider this state, this quantum graph state, this state can be represented by some graph with links and weights corresponding to these parameters. But if we calculate the velocity of this of evolution in this quantum state, we have relation of properties with properties of graph which is constructed on the basis of our G, of our original graph. Just in simple way, we have to square our weights by the weights of in our graph. Then more complicated calculations were done for Hamiltonian in third and fourth power, but we have also very important relation of these parameters, of these properties, of these quantum characteristics with properties of graph. So you can see that we have in this expression we have the elements of adjacency matrix. Also, we have the weights which characterize this our graphs. But let us also write the expression for curvature and torsion and step by step try to find and try to understand the values we have in this expression. So the curvature is defined in the following way. So this is my result for curvature and this is my result for torsion. And in this case, we have S3 and S4. So in this case, we have very nice, very interesting characteristics. S3 represents the product of weights of links which create triangles in our graph. S4 represent the sum of products of weights of links which create squares in our graph. And also here we have N4. This is the same as N2. So this is the weighted degree of the node with index I in graph constructed by raising to the fourth power of the weights of our graph J. So we have a relation of quantum properties with properties of the corresponding graphs. And we can study these properties with the help of quantum programming because if we can find these mean values of Hamiltonian, or we can study the mean value of the operator of evolution. So in general case, the quantum protocol for such studies is the following. So we have to construct this operator of evolution and find the mean value in our initial state. So we have plus states, therefore we consider here these atomar gates, and we have to measure all the qubits in the standard basis. So we considered a particular case, it was Hamiltonian corresponding to a chain, to a spin chain, and we construct this protocol for this particular case. We have 3-qubit protocol, and we studied this mean value for the operator of evolution in the case of this spin system with the help of programming on IBM's quantum device. So the results of quantum calculations are represented by crosses, and the results of theoretical studies are represented by line. Also, we can do in another way, we can find the results of our calculations just considering these mean values in our particular case, and we have that these mean values can be represented with this mean values of sigma z operators. So we can calculate this in very simple way. So very simple quantum protocol for calculation sigma zi, sigma zj, mean value of this product in state plus plus. And on the basis of these results of quantum calculations, we have obtained curvature and torsion. And these values are close to the theoretical ones. So if you are interested in the details of quantum calculations, if you are interested in maybe details of theoretical studies, please look on the paper which just published in Archive. So also the results of studies of the geometric properties of undirected unweighted graphs are presented on the paper published with Laba and Tkachuk. So many thanks for your attention. And I would like to highlight that with the help of studies of quantum states, with the help of studies of quantum graph states, with quantum programming, we can find various properties of classical graphs. And because the results, the relations are quite clear, so we have relation of the curvature and torsion of the relation of the mean value of the Hamiltonian with such complicated parameters, such complicated characteristics of graphs. So we hope to find a way to achieve the quantum supremacy in the future in solving this problem with quantum programming. So many thanks once more again. Maybe you have some questions, comments, please ask.
Okay, thank you very much for your presentation. Let us have some discussion. So do you have any questions in relation to the topic that was presented right now? Maybe I will have one question. So you are using a spin representation in a way for a quantum information processing, right? In a sense, you relate everything to spin operations on a spin. And the question is, can you convert the methodology that you use for single electron devices, because semiconductor single electron devices, because probably you are using the Transmon superconducting qubit, right? IBM quantum experience. So can you convert this to a different paradigm? And the question is, to what extent this would change your results if you use different technology than Josephson junction technology?
So our results, our protocols, and the quantum algorithms we propose do not depend on the realization, because if we have possibility to prepare the quantum state and to measure this quantum state in standard basis, it does not matter for us in what way we have done this. So of course we can, if we can apply the Adamar gate for qubit, if you can measure this qubit, the state of qubit in standard basis, so we can do all these calculations. The same for this case. If we can prepare this operator evolution and measure all the states, we can do this in different quantum devices. Or the same for the attainment. If I can prepare the state and measure, I can do everything.
So the particular
Do you
example.
understand your question correctly?
Yeah, well, yes, but I mean, the case which I was kind of referring to was the case of system of semiconductor coupled quantum dots with
Okay.
with controlled connectivity. So you can have electrostatic gate in between that regulates transmission probability from one quantum dot to another quantum dot, and then I was just thinking how to refer such problem to graph quantum graph studied by you. To what extent I can use the same tools. The question is, do you know any particular quantum algorithms that refer to quantum graphs? Have you tested any quantum algorithms based on the quantum graphs?
I did not, I haven't done these studies, so I just create quantum algorithm for studies in quantum device with these quantum gates, which can be applied. So your question is very interesting. Of course, we can think about performing all the studies in other cases, quantum calculations, and other conditions for quantum calculations. So I have to think, we can think together. Thank you.
Yeah, I will refer to your work, right? Sure. Do we have any more questions from the audience? Please, any comment to the presentation? I was just thinking how to implement this quantum graphs by different technology, quantum technology. And let's say we have right now dominant technologies, IBM quantum experience, right? But let's say quantum dots is another way, and another way is a cold atom. So do you know, can you make any comments about different implementation of quantum graphs by different technologies, quantum technologies?
So right now I cannot share with you the details because I didn't study this in different quantum in this direction. So how to implement this study, how to perform these calculations with different quantum devices. I just created the quantum algorithms and study these properties analytically to find the way how to relate these quantum properties with classical properties, classical graphs. And I use the devices I have access to them. For instance, Rigetti, IBMs, and so on.
I see.
Simulators. So therefore, right now, it's a very interesting question, but I need time to look what conditions do we have and so on.
We have a question from Professor Gleb Skorovatko. Please go ahead.
Okay. Well, I'm doctor. I'm not professor. So, but maybe this is brief comment on Krzysztof question. In principle, I think maybe I'm wrong, but there is a correspondence between spin model and Anderson model. So if you do Jordan-Wigner transformation, so in this sense, probably you can transform this spin model to the language of Anderson model, meaning you have different tunnelings, and these tunnelings between quantum dots probably they can play the role of graphs characteristics or something like that. Right? It's just, I mean, this is just my current thought on this consideration. So maybe this is the way to translate one language to another.
Well, I have one paper in relation to that. Yes, but I was just how to express Ising model in a chain of semiconductor quantum dot systems that are coupled. So in a way, I already have some experience, but it's very interesting for me to convert Professor Gnatenko results into single electron devices, semiconductor single electron devices, to think about this graph theory for such type of devices. And possibly,
very interesting issue.
Yeah. I mean, there is CMOS technology that emerges quite recently and starts to be more quantum. And I know there is a kind of a race in this direction who can do it in case of semiconductors. Do we have any more questions from the audience in relation to given presentation? Let us
just a few minutes. I would like also say a few words. Many thanks for this invitation, and many thanks once again for helping and supporting Ukrainians and Ukraine. Thank you.